Okay, hey everybody. Um, so we have got a huge list of trig identities now at our disposal, our Pythagorean identities, our sum and difference formulas, product to sum, sum to product, our reduction formulas, all these double angle formulas, all the other ones we have, right? So we've got this long list of them that we'll be using. So I want to start practicing using them in ways that are a little more related to what we would really use them for, right? So solving an equation is one place where they might show up, or manipulating a function. So I'm going to start with the simplest here, okay? A very simple uh, um, example where we've got sine of theta equals root 3 over 2, right? So I want to solve this equation. So let's remind ourselves what it means to solve an equation, right? Because one way to approach this might be to say, well, hey, I remember we have these inverse functions, these inverse trig functions that undo it. And so we're left with the input. And then we find sine inverse finds us the angle between negative pi over 2 and pi over 2 that has a sine of root 3 over 2. We can look at our unit circle and find that that is pi over 3. This has not solved this equation, right? So we have a solution, but when we talk about when we're asked to solve an equation, what we mean is to find all solutions. Okay, so the answer I've written down here for this equation so far is wrong. Okay, it's or let's say incomplete. We have not solved it. We've done the first step in solving. We're going to put that to the side for now, for a moment, to talk about finding all solutions. Let's do quick examples. So, for example, we use a lot of our notation a little bit improperly. So, for example, let's just do this. If I ask you what is the square root of 4, the answer is the square root of 4 is 2, because the symbol, the square root of 4, what we mean is the positive square root. It's a function, and it's defined as the positive square root of 4. We know that there's another number that we can multiply by itself to get 4, and that's negative 2, but we're not asking that when we write the square root. However, when I write x squared equals 4 and tell you to solve it, you might be tempted to go, oh, well, let's take the square root of each side. The square root of x squared gives me x. And if we wrote this, again, we're incomplete. It's the same symbol, and the meaning is correct. That's what I mean by the square root of 4. We're using that symbol, but we're using it a little improperly when we solve the equation. What we really want is not the primary square root or the principal square root. We want all the roots of 4, all the numbers that can be squared to give us 4, and those turn out to be 2 and negative 2, right? So there's two answers, x equals 2 or x equals negative 2, okay? So even though we're using that square root symbol, what we really mean is plus or minus the square root symbol, because the square root symbol it means the positive root. But when we're solving an equation, we don't just want that. We want all the possible answers. Or, for example, here's another equation I might give you. X squared minus x equals 6. And maybe by a little guessing and checking, I realized, oh, it turns out if x equals 3, we get 3 squared minus 3 equals 9 minus 3 equals 6. Here's a solution, but we have not solved this equation because there are more answers than this. And that if we actually do a little more work, if I subtract that 6 to the other side and then factor this thing, I see that there are two possible solutions, x minus 3 being 0 or x plus 2 being 0. This one gives us our solution of 3. This one gives us the solution of negative 2. And if we throw that into this equation, we'll see that 2 squared minus negative 2, or oops, sorry, this is negative 2 squared, or 4 plus 2 is also equal to 6. And now we have solved the equation. These are all the equations that are all the solutions to this equation, okay? So just wanted to throw that out there because now we need to think about that in this problem here. So it gets a little more complicated with the trig functions. In these examples I gave, we were solving quadratics, and quadratics can have up to 2 answers. Trig functions are quite a bit more complicated. They can have infinite solutions. So let's start with a unit circle to see why. And in fact, I'm going to move this to the next page so we have lots of room to draw lots of things. So, all right. So here's our work. So starting with the unit circle, whoops, give ourselves a little coordinate system. Looks reasonably good. So what we've found, right, in this first part is that if we have the angle pi over 3, which is about there, this has coordinates 1/2 root 3 over 2. Okay, and so that is where we came up with our result for this equation. But it's pretty quick to see that we can have another solution, right? Over here on the circle, we have another point where, whoops, how did I just plain miss? Okay, so this first angle right here, this is pi over 3. But now we have this bigger angle. This one takes us to -1/2 root 3 over 2. This is the angle of 2 pi over 3. And that by symmetry, right? Remember our little game, if we think, oh, in here, this is going to be an angle of pi over 3, because that's the last third to get to pi. That's going to give us a little triangle, right, like this, which is going to be the same as this triangle over here. That got a little sloppy. But anyways, we know that those are symmetric places on the circle flipped over the y-axis, same coordinate. And so we see, okay, good. We have 2 answers to this equation, but we're not done yet, right? Because I could start here and move all the way around, right? This angle would now be pi over 3. Well, let's think about it this way. We started at 0, we went all the way around, that's 2 pi. Then we went another pi over 3. So that angle also has a sine of root 3 over 2. But then we might think, well, wait, I could go around twice and then that pi over 3. So I could be doing 2, or yeah, let's do 2 pi. There's our rotation, but 2 of them plus pi over 3. There's another angle, right? I could go around 3 times, 2 pi times 3 plus pi over 3, and keep getting that. I could go backwards. There's a rotation, but let's multiply it by -1 to go backwards. Or 2 pi times -2 plus pi over 3, right? That would be starting here, going in the backwards direction, negative, but then, oops, didn't want that to happen. So we go -2 pi and then forward pi over 3. I know this drawing is getting to be a mess, but I hope you've got the idea of how we can move about this, the unit circle a little bit. I can keep doing this, right? I can keep doing this. And so any full rotation in any direction plus pi over 3 will always land me in that spot, okay? So our solutions, well, we're going to have theta equal to pi over 3, or positive pi over 3, plus a full rotation or any multiple. So multiplying by k, where k is an integer, right? So there's just any whole number, including the negatives and the positives. And so this piece right here just represents rotations, full rotations, right? And some number of them. It doesn't matter the number, right? So there's an infinite number of solutions. Also, we can do the same thing for this other answer, right? For this other answer, we can go right backwards, forwards, around a whole bunch of times and keep doing this over and over and over again. So we also need 2 pi over 3 plus 2 pi. I don't really need the parentheses, where k is an integer. Okay, so if we're solving an equation, just in the most general way, this is how we get a full solution, right? We have to consider the unit circle and think about what points on the unit circle. Like what I usually think about is just I look at my unit circle, the ones we list on the unit circle, right? Between 0 and 2 pi. And I find all the thetas on that picture. And then I start adding 2 pi full rotations. We'll see in some cases we might just add a half rotation for things like tangent and cotangent, and some other certain cases where that might be the case. But we have to figure it out from the geometry of the situation, and then we write all of our, I would say, like base solutions, and then these full rotations. Okay. We can also think about this in terms of the graph of sine. So here's our coordinate system, sine. Oops. This is not a great drawing, but it's something, right? We were looking for solutions to where is sine equal to √3/2, right? So I'm just going to draw, say √3/2 is here. It's the output, the y value. And so the solutions are everywhere this line intersects. And so we see points here and here and here and here and here and here. This is the one at pi over 3. This is the one at 2 pi over 3. And then we can add 2 pi to get here. Let's do it in another color. Or we can add 2 pi to get here, right? Or we can subtract 2 pi to get here. Or subtract 2 pi to get here. And then we can keep doing that. So there's all these solutions extending out in both directions. All right, so we have to be a little bit careful about these. Let's do one last example in this video. Let's say, for instance, just one example where it's not 2 pi. So there are many reasons why it might not be, but what if we had this one, sine of theta is equal to -1? Well, our base answer, theta is -1 at, we can write it as 3 pi over 2. We could also write it as -pi over 2. I'm going to do that one, -pi over 2. And again, we can think about full rotations. We can keep going around the circle. 2 pi k, k. So I'm just going to write this like this. This means k is in the set of integers, right? So even if you're not familiar with this notation, this is just a little symbol to mean is a member of or is in the set, and this fancy z is the integers. I think it comes from a German word, but I'm not 100% sure on that. There's a German word that means digits or something that begins with believe. Regardless, just means the same thing as this sentence up here. So -pi over 2 plus 2 pi k. We don't have a second answer like we have here because there's no other place on the circle. This is one of those special places, right? There's no like mirror image across the y-axis that has that, because it's on the y-axis. And so in this case, we only have one answer, but one base answer, but we still have an infinite number of answers, right? This is all of these minimums that we can keep finding as we go forever and ever. Right, and notice I'm choosing kind of simple base -2 plus 2 pi k. I could have chosen 3 pi over 2, or I could have chosen, right, this one out here, or I could choose one out at, you know, hundreds of halves of pi out there and choose one, because you're getting an infinite number of rotations. It doesn't matter where you start, but we usually start at the simplest one. Okay, that was enough for this video. We'll do lots more solving trig videos, but solving trig equations videos, but this gets us started. Thank you, everybody. I will see you next time.